First I would like to thank the organizers, especially Arnab, for organizing this really fantastic meeting and for inviting me to give a talk. I'll talk about KPZ physics in integrable spin chains. So this is work done with these people, Dipankar Roy, who's postdoc at ICTS and who's really done, most of the numerics that I'll talk about. It's really beautiful numerics done by him. I think he's there in the audience somewhere. Abhishek Dhar, a former student of mine, Manas Kulkarni, colleague at ICTS, and Konstantin Khanin and Herbert Spohn. Okay, so this is the outline of the talk. I'll first give a sort of very quick introduction to KPZ universality. And then this is a set of work that we have been doing for the last few years that I'll talk about. So I'll get 1 minute extra. Yeah. Okay, so so this is basically we are discussing classical integrable spin chains, and one of the interesting things that's been discovered in this integrable spin chains, both quantum and classical, is the observation of KPZ signatures of KPZ physics, and this shows up in like dynamical correlations in equilibrium, and I'll talk about these results. It also shows up in if you drive the system out of equilibrium and prepare steady states with boundaries at different temperatures and different magnetic fields. So this is non-equilibrium steady states. And then I'll discuss about some how do you explain this anomalous spin transport in these spin chains. So there's been some recent work trying to use nonlinear fluctuating hydrodynamics to understand this anomalous transport. And I'll discuss some of our work on this. Okay, so KPZ equation basically describes the hydrodynamic behavior of a growing, let's say, 2D interface. So some interface is growing. So it was first written in this paper in 1986. So this is the equation. So this is the height as a function of space and time, just one dimension. And so there's a diffusion term, there's a nonlinear term, and there's noise. Okay, so if you make a transformation from this height variable to a density variable, then the equation that from this equation you basically get what's known as the noisy Burgers equation. And this has a conservative form, so it's essentially they describe the same physics. Okay, and a simple way to see this. Okay, so let's say this is an interface, and which is growing in time, and this mapping can be understood from a very simple model called TASIP. So this is a one-dimensional model of particles on a lattice, so every side can have just one particle. And the dynamics is that every particle hops to the right with a rate 1, and it can do so only if it's an empty site. Okay, so this is a 1D lattice model called the TASIP, totally asymmetric simple exclusion process. And if you just make a mapping that whenever there's a particle you put a down slope, and when there's a hole you put up slope, then this particle model gives rise to a interface, and that is basically this mapping here. And so you can see that interface can be also thought of as a particle model. And both are described by the KPZ physics. Okay, some other models which are described by the same equations is some model called ballistic deposition. You just deposit particles randomly on a surface, and whenever particle comes and sees it, another particle just sticks to it. Okay, so if you evolve this for a long time, you see a interface like this. So this is the interface. And there are two interesting things about the interface. It's a rough interface, which is characterized by two length scales. One sort of spatial length scale, which grows as t to the power 2/3, which says how space points are correlated in this interface. Okay, so this grows as t to the power 2/3, and then you can ask how do the height. So the height grows linearly with time on an average, and the fluctuations goes as t to the power 1/3. Okay, so these are the transverse fluctuations. So there are these two important length scales. So this has been observed in many experiments, and especially some beautiful experiments by Takeuchi and Sano, where in turbulent liquid crystals, where this is the experiment, you look at the interface and you compute things like current fluctuations and so on, and you verify many of the predictions from KPZ physics. Okay, so there are a lot of other models which also follow under this same university. Okay, this is just a video that I found on YouTube. It's just on your windscreen, there's ice, snow falling, and you can see the interface. This is basically almost the ballistic deposition model. You can see a nice interface growing, and this is the physics one is trying to understand. Okay, so this is actually, there's a nice website which describes a lot of this simple thing. Okay, so now KPZ universality is characterized by two things which I already mentioned. There are two sort of length scales, and one is you just look at space-time correlations. Let's say this is the height function, and you take a derivative which is the density field, and this satisfy a universal scaling form. So this is the two-thirds scaling, but this function itself is a universal function. Okay, so it's a known function which is tabulated somewhere. And then you can look at the height fluctuations, and it grows on an average with a linear time dependence, and the fluctuation scale as T⁻⁴. If you look at the fluctuations of this at this scale, then they satisfy again universal scaling function, which depends on the initial condition with which you start the interface. So it's Tracy-Widom for flat or wedge initial conditions, and it's Pike-Raines for stationary initial conditions. Okay, so these are the two things that are sort of very characteristic of KPZ physics. Okay, now we come to integrable quantum spin chains, and so this is the model that we are thinking of, just Heisenberg spin chain with an isotropic parameter delta, and this is an integrable model. It's solvable by Bethe-Ansatz, but it has very surprising transport properties. So if you define a correlations function between spin-spin, which just tells us if there's a perturbation in magnetization somewhere, how does it spread? This has the following scaling. So there's a gapless phase for delta less than 1, where it's just ballistic spreading. Okay. In the, sorry, this should be a gapped phase, delta greater than 1, sorry, so this is a typo. It's a gapped phase, delta greater than 1, you find diffusive spreading. It just spreads like a Gaussian. And then at the isotropic point, you find, in fact, that it has KPZ scaling. So this is super diffusive spread of perturbation. And actually what was found is that in this, I think this was the first paper where this was seen in a quantum, in this model, that this function is actually exactly identical to KPZ, the KPZ scaling function. Okay. So there are two things that you should notice. One is the exponent, is the scaling exponent is T⁻², and the scaling function itself agrees completely with KPZ. That's the sort of big surprise. Okay, so I'll now talk about one of our first question. Yeah. 1D, everything is one dimension. There's no, I don't think there's an exact mapping, but it turns out it's quite remarkable that the classical and quantum, I mean, if you take a quantum integrable chain and a classical integrable chain with the same symmetry, like spin symmetry, then they show very similar behavior. Okay, so this is what I am showing now. It is a classical integrable spin chain. So if you take the standard Heisenberg spin chain, it's not integrable. But if you take this particular interaction log of 1 plus s dot s, so this was, I think, first studied by Ishimori and Halden, and independently, and this somehow turns out to be integrable, this very strange interaction. And again, you can look at the spin-spin correlations. Okay, so in this paper, this is what we numerically computed at finite temperature and at zero magnetization. And so this is how the spin fluctuations spread. And you see that we have scaled by x by T⁻², and it collapses perfectly. Okay. And actually on this linear scale, if you compare with a Gaussian and a KPZ scaling function, they both seem to agree very well. But on the log scale, you can see that the KPZ function does much better than the Gaussian. Okay. So this is again a demonstration that even the scaling function is perfectly KPZ. It's at the isotropic point. So this model is already at the isotropic point, exactly, delta 1. Yeah, so this model also you have the corresponding versions where you have delta less than 1 and greater than 1, and you correspondingly find either diffusive or super diffuse or ballistic transport. Okay, on the other hand, if you look at energy correlation, so you can also compute this energy-energy correlations. There you find that it spreads ballistically that you would normally expect in an integrable model. Okay. So spin and energy transport are very different in this model. Okay, so actually there were earlier work on this classical model where it was shown that the current autocorrelation shows KPZ scaling. Okay, so in a more recent work, what we looked at is what if you add integrability breaking terms. So this term is the standard Heisenberg spin chain, and it's for the classical system, it's non-integrable. Okay, the same system in quantum mechanically, if you take spin half, that's integrable, but the quantum version is non-integrable. And we asked, what if you add this term to this integrable part? Okay. Now, so here we look at the second moment of the correlations, and for different strengths of this perturbation, for lambda equal to 0, we saw that this spreads as to a 2/3. Quite remarkably, for different values of lambda up to even 1.5, you find that this still scale, the super diffusive growth is still visible. No, this is always gapless, right here. Okay, so on the other hand, if you look at energy transport so this was ballistic, but as soon as you put this lambda, you find that it becomes diffusive, as is expected for a non-integral model. Okay, so energy becomes diffusive, but spin somehow persists in being anomalous. Okay. And these are the correlation functions, and we find that even at when this integrality breaking parameter is 1.5, the correlation function is still KPZ. Okay, and it's distinctly different from Gaussian. On the other hand, the energy correlations which were ballistic in the absence of this integrality breaking term now become clearly diffusive. Okay, so which means this is quite large. I mean, really, the integrality, yeah. Yeah.
How is it perturbative breaking?
No, it's highly non-perturbative. In fact, right now, right? Yeah. So I'm calling it perturbative, but what I mean is it's an extra term. So this is actually highly non-perturbative, which is why you can see that the energy correlations change completely, right? It becomes from ballistic to diffusive, but the spins are very robust. I mean, somehow it still works. Okay, so now I'll come to so far I discussed correlations in equilibrium. Now I come to the non-equilibrium situation where you take this spin chain and connect reservoirs at the two ends. You can put reservoirs of both energy and magnetization, right? So different magnetic fields and different temperatures. Okay, so this was again studied in the quantum context very long time back. I think this were probably the first papers which saw signatures of anomalous transport. In this paper by Marco, I mean, so he took a chain and connected to Lindblad baths with different magnetic fields and at infinite temperature. And what he found is that the current scales with system size as 1 by square root n, and you actually get some sort of this strange temperature profile. Some highly, so there's some non-analyticity here, but this funny kind of temperature profile. So this was for where the difference in magnetic field was kind of small. If you put a strong drive, then there's this paper by Tomaz where he in fact shows analytically that the current scales as 1 by n square. Okay, so this very different scaling depending on how you drive the system. Now we ask the same question in the classical case, what do you get? Okay, so in the classical case, of course, you can do much bigger system sizes, that's an advantage. Okay, so now there's a surprise from in what we see in this number. So what you see in this non-equilibrium experiment is actually connected with what the two-thirds scaling that you see in the equilibrium simulations via Green-Kubo. Okay, so what Green-Kubo tells us is that the conductivity is given by current-current correlations integrated. So at the isotropic point, the current-current correlation scales as 1 by t to the 2/3. And of course, if you do 0 to infinity, this diverges. But one can argue that this upper cutoff should be fixed at the system size divided by typical velocities in the system. And this would imply that the conductivity scales with system size as L to the power 1/3. And so the current should scale as 1 by L to the power 2/3. Okay. So this is the kind of arguments that typically is used in systems of like the Fermi-Pascagoulum and other anharmonic chains, where one again connects equilibrium properties with non-equilibrium transport properties, and this usually works. Okay, so this is of course a sort of there's some physical argument why you put L here, but this typically works. And so from the same argument in this, yeah.
Is it still at the critical point?
So I will always discuss the isotropic point right here. So therefore we expect this kind of power law dependence, but this is different from what has so far been seen in quantum spin chains. Okay, so this is what we wanted to investigate in the what happens in the classical case, and so this is this recent paper. Okay, so we are studying again this Ishimori-Haldane chain, which is this with the log potential, and we drive the boundaries at different temperatures and magnetic fields. Okay, so yeah.
Does it work? Yeah.
Yeah.
So I mean, why do you? What's the motivation to integrate up to L over VC? Because there is no ballistic part of the spin correlate, current correlator, right?
Okay, so I mean,
maybe you should not integrate until L over VC, but until you hit the end of the light cone, which is spreading.
Yeah, ballistically. Okay, so usually there's a ballistic component, right?
Usually there is, but here it is not. If it's zero magnetization, there is no.
Okay, because okay, yeah, right, yeah. Okay, perhaps that's.
We can discuss it later.
Right, yeah, maybe, yeah, we can discuss. Right, okay. Okay, right. So yeah. So anyway, this is what we are doing. So we take this spin chain, and the boundary spins are connected to heat baths in some way. So basically, what we do is we take pairs of spins and evolve them via Monte Carlo, which tries to equilibrate them at a given temperature and magnetic field. So with this, we do this at both ends. And in this case, actually, we can verify that this dynamics, if you put the same temperatures and same fields, it actually goes to the equilibrium state. Okay. So in quantum case, finding good baths, of course, is a big problem. But in the classical case, one can do this very easily. And okay, so this is what we do. And let me show you the results that we find. So in this case, we actually find that the spin current, so here the spin current is plotted versus system size. So the green curve is the Ishimori-Haldane chain. And here you find that you get this 1 by L to the power, it seems to at least to give this two-third exponent. Here what we plot is the running slope as a function of system size, and the green curve, I mean, okay, so at least it seems to be far from 0.5, and it goes, so this is two-third line. So at least our data seems to indicate that you get this 1 by L to the two-third exponent. On the other hand, if you look at energy current, then it's completely independent of system size. This is the line. So I won't discuss these other lines, which are if you add the integrability, breaking, perturbation, and so on. Yeah. We always do weak drive. We put a small magnetic field difference because It's known that if you are not in the zero magnetization sector, then you can get the transport properties change. Okay, you don't get the anomalous scaling. So we always put a very small magnetic field difference. This is translation event right here. At the boundaries, no, yeah. So boundary conditions. I mean, typically for anharmonic systems, the system size scaling typically does not depend on boundary conditions. But okay, I mean, one doesn't know. Yeah.
Is there, it doesn't matter that you are taking m equals to 0 sector or not.
No, there it does matter.
Doesn't
Right, yeah, you have to be in the zero magnetization. Okay, so we also looked at, so these are other things that you can check in this non-equilibrium in steady state. Like how does the magnetization profile look? That looks like this. It's like has some nonlinearity, and while the energy profile is completely flat. The other thing we also looked at is typically in this non-equilibrium steady state, you get what is known as long-range static correlations. So if you look at the middle spin and how is it correlated with some other spin, then this scales as it has a 1 by n scaling. Okay. Yeah. In the total, if it becomes non-integrable, then of course you have diffusive, because it becomes non-integrable if you have pinning. Right, yeah, but it's for a if you have momentum conservation, then you expect anomalous transport, right, yeah. But here it's anyway, there's no momentum conservation, right? Yeah. Okay, any other questions? No. Okay, so let me quickly go to the last part. So, yeah, so the summary of this integral spin change is that KPZ universally class is characterized by these two quantities, and so far I have discussed this part, just space-time correlations, and we have seen that in most of the simulations, both quantum and classical, they show both KPZ scaling, which is this 2^2 dependence of the length scale, and also the scaling functions agree exactly. Okay. Now, if you look at the current fluctuations, so these height fluctuations are related to, like, if I take the spin chain and ask, like, if I look at one point, if I ask how much magnetization is transferred in a given amount of time, and the fluctuations of this quantity, that's related to these height fluctuations. So this has been computed again, and what one finds is that, okay, so this, last week there was a talk by Pedram from this Google experiment on using a quantum computer, where the conclusion was that you don't see KPZ scaling for the current fluctuations. And there are some very recent paper where also from this classical simulations, it looks like you don't get a KPZ universality for the current fluctuations. Okay, so now what is a possible theory to describe this? Like, how do you understand this anomalous transport at this isotropic point? So there has been a lot of phenomenological theories by various people. And most recently, there's been this idea of using writing effective hydrodynamic equations for the fluctuations in magnetization, which is coupled. So this is an integrable model. There's an infinite number of conserved quantities. But can we write some sort of simple set of equations for a few hydrodynamic fields? So this was what was attempted in this paper. And they wrote a set of equations described where there are just two fields, the magnetization and something which is like a velocity field, which is related to the difference between giant these quasi particles moving to the right and left. Okay, so this is effectively like some velocity field, and these were the equations that they wrote. Okay, so so this is as diffusion and noise. But the important terms are these nonlinear terms. So the magnetization couples with this other field, which is like it just advencts the magnetization. So I said phi is like a velocity field. And phi itself depends on m square, and then you can also keep this term phi square. Okay. So this is these equations you can also argue in terms of like what's the basic like the minimal model which puts in nonlinearity, but sort of it takes into account the symmetries of the system. Okay, so so I'll call this paper DGV. So the derivation is based on kind of hydrodynamic GHT equations, and they try to incorporate the role of giant quasi-particles which play a role in this anomalous transport. And their main results are that they show that this coupled KPZ, the spin correlations have a KPZ form, and the current fluctuations is like the sum of two bike range distributions. Okay. Okay, so I just want to say that this is actually similar to what was used in to understand current fluctuations in Fermi-Pastel chains in earlier work. Okay, so now what our motivation was basically to understand these equations in some more detail. So these equations actually first appeared in a very old paper by Artas and Dhar. They were trying to understand polymers in random medium with some electric fields. And in their case, these two equations correspond to the parallel and transverse fluctuations of the polymer. Okay, so okay, and so the general structure of these equations, so we have two conserved fields, U1, U2, and in general they satisfy a continuity equation like this. And then you can define something called a flux Jacobian, which is just derivative of this, the current with respect to the fields. Okay, so now the eigenvalues of this matrix, so you have two modes, and you can ask like if I perturb a bit, how do these modes, what do these modes do? So typically they would travel with some speed, and the eigenvalues of this matrix give you the speed of this of these modes at just linear order. Okay, so now, so the specialty about this, the present equations is that both the modes are stationary. Okay, so their speeds are exactly zero, which is what we call this degenerate flux Jacobian. Both the modes have the same speed. In this case, both are zero, and so you expect that these two modes interact very strongly, and so it's a question whether you still expect KPZ physics to be observed or not. Okay, so yeah, so this is the general structure of the equations that we study. There is this coupling, the nonlinear term, and these G matrices are describe the nonlinearity. Okay, now, okay, so this is what I said, that in this case where the eigenvalues of A are degenerate, the modes interact strongly, and it's not clear usual predictions of nonlinear fluctuating hydrodynamics will apply or not. And this is the case of interest here. Okay, so for certain choices of the G matrices, it turns out that the stationary state fluctuations are Gaussian, and DGV basically studied this class. This is the simplest class that one can study, and so this is what we will also focus on. Okay, so it also turns out that there's a so earlier I talked about the asymmetric exclusion process, and there's actually a two-lane TASIP model, which again leads to exactly the same hydrodynamic equations as given here. Okay, so that's also sort of an interesting thing, that there's another model which is in the same universality class. Okay, so we basically wanted to do a yeah.
When this giant quasi-particle, that coupled equation, they wrote those, that is for the integrable point, right? Which is protected by non-abelian symmetry, means the XXC.
Yeah, I mean, so it's always at the isotropic point. So but I think at the other points also they play a role, but it's mainly at that point. Right?
But for this, you also study the integrability breaking perturbation. Also, that you.
No, here I just stick to no. Right, yeah. Okay, so I will now describe a numerical study of, so what we studied is both the TASIP system, the lattice model, and this coupled Burgers model. Okay, So, and I'll just show the numerical results. So these are the, finally, if you map to the height model, these are the equations that we solve. And if you, one of the heights doesn't grow with time, the second height evolves in time, and this is what it looks like. Here, this is a simulation where you start with a flat initial condition, and you can see the surface kind of roughens and moves with some speed. And we are trying to understand correlations in this direction and fluctuations in this direction. Okay, so so there are two components, and now these are the space-time correlations in this model for the first component, and so you can see that they satisfy this KPZ scaling extremely well, and you get convergence at very short time scales. But actually you don't, at least so far in our data, we don't see convergence to the KPZ scaling function for both the components. Okay, so this is the second component, the phi field, and both these fields don't seem to satisfy KPZ scaling function. KPZ scaling is satisfied perfectly, and that is something we expect, but the scaling functions are not, it's not clear that they are KPZ. Okay, then we looked at current fluctuations, which is related to height fluctuations in the KPZ picture. And in this case, okay, so the first component, it's a symmetric distribution which just follows from the symmetry of the equations. It has the symmetry, m going to minus m is symmetry, so this is what we get. And the second component has a distribution which is very close to the bike range distribution. Okay, so this is dashed line is the bike range. It is very close. Okay, so the first component, which is corresponds to magnetization, if we compute the the kurtosis, then for bike range it's 0.289, and for this particular model we get 0.152, which actually can be understood as the sum of two bike range distribution. Okay, so in this case, this is similar to what was predicted by the people who proposed this model. But actually, it turns out that the actual spin model doesn't really seems to satisfy this. Okay, so the actual spin model is very close to Gaussian, in fact, and in that sense, this doesn't seem to describe the spin system. Okay, so I'll just tell you about the lattice model that we studied. So it's two lanes, and you have particles hopping to the right on this lane and particles hopping to the left on this lane. Okay, so this is like cars going this way and that way, and the rates actually on this lane depend on what you see on this lane. So it's usually 1, but on some sites it's gamma if the configuration out here is like this. Okay, if it's 1,0 here, then this guy hops with a different rate. For any other configuration on this side, it's always 1. Okay, and similarly on this site, on this lane, you have a similar dynamics. Okay, so this is gamma is less than 1, right? Yeah, less than equal to 1. Sorry. Yeah, this equation, I mean, this model, you can write the hydrodynamic equations, and it's exactly the same equations that so you get at the coarse grained level, it's exactly these equations. Okay, and of course, when you go to hydrodynamics, you make assumptions and so on. So it's not clear that you should get exact agreement. But in this case, quite remarkably, what we find is that this produces, I mean, exactly the same correlations and also the current fluctuations as the continuum model. Okay, so here to make this comparison, we have to do some rescaling of time. That's one sort of fit that we use. But then with the single parameter, we fit the complete functions, so which is quite, I think, remarkable. Okay, so
model, this is not integrable.
Lattice model. Okay, so see, these are stochastic processes, and integrability is like definitions are kind of different. Okay, so therefore we see kind of very nice universality between these two lattice and continuum models. Okay, so I think I'm done. I'll just summarize. So I discussed anomalous. Okay, maybe I'll just leave this and take questions.
Thank you, Abhishek, for this very nice talk. Questions? Thomas, do you have a... Yeah.
Does it work? Yeah. So I wonder whether you tried, or maybe it would be interesting to try to look at fluctuations in integrability broken model where it still shows very nice KPZ scaling function. Would you expect? I mean, did you try to look at fluctuations there? Because I wonder whether they would still be nearly Gaussian.
You mean current fluctuations?
Yeah, spin current fluctuations. Yeah.
No, we have not yet looked at, right, yeah. You're saying you still expect whether they remain Gaussian or not?
Yeah, or maybe they would be closer to this model.
Okay.
Because it's just two modes.
Right, okay.
I mean, there was some intuition that integrable systems would not work like this because there are in fact infinitely many modes, not just...
Right, okay. But you think if you break integrability a bit, then it might actually work, right?
Yeah.
Okay, yeah, that's good.
Any more? I thought I saw questions. Oh yeah, right. Do you have it?
Just a quick question. I'm sure you mentioned it, but to make sure. So in the quantum Heisenberg model, there's KPZ scaling, but then the current fluctuations, as you said, they don't have like KPZ scaling. What about the classical version of that model? So is it the same, or do also the current fluctuations have KPZ scaling?
I think that's what Tomaz has studied. They studied a different classical, but it's a classical model, and they find that the current fluctuations don't satisfy KPZ.
So it's basically there's a one-to-one correspondence.
For the yeah. I mean, but for the quantum, I think there's only the Google experiment, right? Is that right? I think that's there's no other direct simulation.
Thanks.
So why did you choose this model, not Heisenberg classical model, or what is the...
With the Ishimori held it. That's integrable. The usual Heisenberg is not integrable.
Okay.
So I'm not a specialist of this, but does one expect any difference at the hydrodynamic level between classical and quantum in general?
Okay. Okay, in general, at the hydrodynamic level.
Yes.
Yeah, I don't know. I mean, it seems to me for integral models, it should be very similar, but maybe for non-integral models, there might be different. But at the hydrodynamic level, maybe they should always...
Because it's difficult to imagine terms that are at the same time inherently quantum and survive the hydrodynamic limit, no?
Right, yeah. Yeah, okay. Yeah, I think that's an interesting question, but I don't really.
Okay, so if there are no more questions, then let's thank Abhishek and all speakers of the session once more.